The architecture works with movable systems that extend and retract the tools within it. First, the drill is extended through extension rods and pistons out of the architecture. Sensors will detect when the hole has been dug to an adequate depth for ice to be retrieved, and then the heat exchanger will unwind from the tube assembly and be placed into the hole to heat the ice into water as the drill is retracted back into its idle position. This melting is done through recirculated hot water that is heated by solar arrays located on the top of the architecture. The heat exchanger is then retracted back into the architecture, and then a pumping and extraction mechanism is placed into the hole to retrieve water through a pressurized gas line purge system that drives the fluid motion necessary for pumping, and the mining and extraction process is complete. The water retrieved is stored in a tank on board the architecture for later use as a propellant.
A methane-oxygen propellant will be produced through three main components: a compressor, CO2 reducer, and a water electrolyzer. The Sabatier method is used to produce the methane and oxygen needed. An optimal 3-to-1 ratio will be achieved through utilizing the water extracted through the gas line purge system.
So once the methane gas and oxygen is produced, it will be compressed and stored into cylindrical aluminum tanks. The tanks will be strong and durable enough to prevent any leakages and be stable for a long period of time. So each cylindrical tank is about 250 cubic meters. So one tank can store 2 years worth of propellant. The cost for one processing system will be about $350 million. However, to deliver all of the units' weight to Mars, that will bring the total up to $7.5 billion per unit.